We continue our discussion of DC-DC converter with step-up converters. They are also very often called boost converters. As I already mentioned, with step-up converters we are able to obtain an output voltage which is larger than the input voltage we have available. And of course also in this case the typical use of step-up converters is in DC power supplies and in the driving of DC motors. And again, a typical step-up converter has the same components that we have seen also in the step-down converter. We have basically inductors, capacitors, and switches. Of course, they are arranged differently. In this particular case, the arrangement is the following. We have the inductor, and then we have a switch here, and this is V in. The switch is S, then we have a diode and a capacitor, and then at the output we have the load, which we can represent as a resistor for simplicity. So this is the load. The load is not a resistance, it's just the simplest possible load. Okay. The voltage on the output is VO, and the current is IO. The current in the inductor is IL. So we have that VO is larger than V in. This is the main point. So of course the switch can be on or it can be off. Let us have let us grasp the behavior of the converter. The thing is the following. Basically, when the switch is on, we charge the inductor, which means we store energy in the inductor. You see that when the switch is on, the voltage applied to the inductor is exactly Vin, and therefore if you have in an inductor a constant voltage applied to the terminals, the current increases linearly with time. Okay. And the energy in an inductor is 1/2 L times the current to the power of 2, and therefore when you increase the current in the inductor, you increase the energy stored in the inductor. Okay, so let's write the two phases. Switch is on. The voltage applied to the inductor is equal to V in. Let's call it this VL. So L accumulates energy. Remember that the energy accumulated in an inductor is equal to 1/2 Li to the power of 2. So when we increase the current, we are accumulating energy in the inductor. And of course, this energy is taken from the input generator. So we have a transfer of energy from the input generator to the inductor. On the other hand, the diode D is off because the cathode is at 0 voltage since the switch is on, and this means that the load is only connected to the capacitor C. Okay? Load is only connected to C, which means that we have the capacitor which discharges through the load. Okay? Now we have the other phase when the switch is off. We have a different situation when the switch is off. What basically happens is that we are trying to remove current from the inductor because we are, let's say, detaching the input voltage from the inductor. And what happens is that this voltage increases until the diode starts to conduct and the current flows in this direction. So what we have is the diode goes on and the load no, not the load, the inductor. Sorry, the inductor L provides current to the load and also to the capacitor. So the loads accumulate energy when the switch is on and discharges the energy when the switch is off, and the capacitor does the opposite thing. When the switch is on, the capacitor loses energy because it provides current to the load, and then when the switch is off, the capacitor gets charged by this current coming from the inductor. Okay, this is a quite qualitative description. Of course, we can evaluate what happens in a more quantitative way. You should be able to notice then when the switch is off and the diode is conducting, the voltage applied to the inductor is this voltage minus this voltage. If we discard the voltage drop on the diode, this node is at VO. So VL is equal to V in minus VO. Okay, that is also useful to write. So let's consider the situation again, and now a bit more quantitatively. We would like to, let's say, understand what is the impact of these various components on the voltage ratio, on the ratio of the output voltage to the input voltage, and also on the behavior of the overall circuit. So let's do it a bit more qualitatively. Let's draw the behavior of the voltage on the inductor. So what we have said is the following: when the switch is on, okay, the voltage on the inductor is equal to V in, and then when the switch is off, let us assume that this is the point at which the switch goes off. When the switch is off, the voltage is V in minus VO. Now, in stationary conditions, we have a periodic behavior. So this means that we have a fixed duty cycle, and the switch stays on for a certain time and stays off for another well-defined time. And this is going to be, if this is 0, this is going to be the period, the switching period. Now there is one observation to make, and it's the following. If I draw the behavior of the current in the inductor, also the current in the inductor in stationary conditions must be periodic. So the current in the inductor is determined by this equation, which is the equation that defines an inductor. And this means the following. Then, of course, when V is positive and constant, the current in the inductor increases linearly with time. When V is negative and constant, the current in the inductor decreases negatively with time. So, during the time during which the switch is on, we have that VL is equal to V in, and therefore we know that the derivative of the current, let's draw it here, as a function of time is equal to V in over L. This is the IL over dt. Okay? Now, in stationary conditions, the behavior of IL must be periodic, and therefore during the time during which the switch is off, the current must go down to the initial level. So must behave in this way. During this period, VL is equal to V in minus VO. V in minus VO over L is equal to DIL over dt. So from this we learn something, and of course we learn that VO must be larger than V in, because this term to the numerator of this ratio must be negative. Okay? So this is the reason why in stationary conditions the output voltage must be larger than the input voltage. And the reason is simply that in stationary conditions the current must be periodic with period t, and therefore from the peak it must go down, and in order to go down the derivative must be negative. Okay? So this is why I did not draw the profile of VL as a function of t, because I wanted to explain this fact before putting here a level V in minus VO smaller than 0. Okay? If I did it before, it would seem arbitrary, but now that I have explained that we need the current to go down, of course, it's clear that this difference must be negative. Okay, now, so let's call this period T on, as we have done already for the back case, which is equal to the duty cycle times T, and this period we can call T off, which is of course the complementary duty cycle times T. Okay, and of course now we can write an equation which is pretty simple. This quantity, the increase, let's compute the total increase in the course of a time period of the current. The total increase is 0. So, and the total increase is the following. The derivative of the current in time times the time, which is V in over L times dt, which is T on, plus the variation during the subsequent T off, which is V in minus VO over L. This is the derivative times the duration of T off, which is 1 minus D times T. So this is the equation that we get. So the only condition in order to write this equation is that IL at T is equal to IL at 0. And from this, we have this expression. Of course, from this expression, you can see that we can derive the relationship between VO and V in. Okay? And that's pretty easy. We can simplify everything, and of course we can put VO on this side. Here we have VO times 1 minus D is equal to V in, and that's it, because we have V in times D plus V in times 1 minus D. So we are left only with V in. And so we get VO over V in is equal to 1 minus D. To 1 over 1 minus D. To 1 over 1 minus D. Okay, so this is pretty easy to derive from a coordinate point of view. You need to clearly understand what happens. Of course, you can see if we just look at the final expression, of course we know that D is a duty cycle, and therefore please notice that D is a number which is between 0 and 1. And therefore, the ratio V out over V in is something that is larger than 1. It can go from 1 to, in principle, a very large number if D is small enough. Of course, we have considered really ideal conditions. And of course, this means that we are discarding all non-idealities. In practice, it's really hard to have a voltage conversion ratio that is larger than 10. So in principle, if you take D close to 1, you can go up to infinity, but in practice, it's very hard to go beyond 10. Okay. So for with the buck converter, we can stay below 1. With the boost converter, we can go above 1. Okay. Of course, this is a particular case because it's the case that when we have discussed the buck converters, we have called continuous conduction. Because you see here in the inductor, we have a continuous current. The current is always positive. Of course, this is true up to a certain point, because let me go back a bit. The current that goes through the inductor during the current that goes through the inductor during the off, when the switch is off, is also the current that goes through the load, right? So what we can write is the following: the average current that goes through the inductor during T off is also the average current that goes through the load. And this, of course, has an effect, because if we reduce the current absorbed by the load, we reduce the average current through the inductor, and therefore, let me go here, we move down this line. When we move down this line, we can get this below 0 and arrive in a situation in which the current in the inductor is not positive. It's not always positive anymore. So we need to investigate this situation a bit more. Let me just do it. Before we do it, we should do the following thing. We call this situation continuous conduction mode in order to distinguish it from the continuous conduction. How can I? Okay. So let's assume that we are reducing the average current in the inductor. If we reduce the average current in the inductor, we move down this line, and at some point we reach the horizontal axis. We reach a position in which a situation in which the minimum for IL is equal to 0. That is an important thing to understand because we cannot go below that. You should consider that during T-off, the current IL goes through the diode. Let me show you again this plot. You see here, IL goes through the diode. But of course, if IL would go below 0, the diode cannot conduct in the other direction. Okay? So, basically, if IL would go below 0, at some point, when IL is more or less 0, the diode would go off, and therefore IL would stay at 0, but would not go negative. Okay? So let me show you. Let me describe you first the boundary between the two situations. Boundary between continuous and discontinuous conduction. Of course, at the boundary between continuous and discontinuous conduction, IL goes exactly at 0. So it's like this when it goes up, and it's like this when it goes down. Let's assume that this is T. So this is T on, and of course this is T off. So this is the peak, and the derivative here of the current is V in over L. So the peak current is V in over L. This is the derivative times T on times dt. T on is equal to dt. And the average current at the peak is equal to, we call it ILB, where this B stays for boundary, is equal to 1/2 of the peak current. This is exactly the same type of reasoning that we have done for the buck converter. So we have written it. We can write it as a function of the output voltage, and therefore, since the input voltage is the output voltage times 1 minus d, we can write it in this way. Okay, so you see the boundary current in the inductor between continuous and discontinuous conduction is a function of the output voltage of the duty cycle and of the switching frequency. This is the period of the switching period, which is of course the inverse of the switching frequency. Okay, the average output current at the boundary is IOB, the output current at the boundary, is equal to a fraction of the current in the inductor, because the current in the inductor goes at the output only for a fraction 1 minus d of the total period. So this is ILB times 1 minus d. Okay, this is a critical point to understand. Only, let me repeat it, the current in the inductor goes at the output only during T off. So the average current in the output is equal to the average current in the inductor times the complementary duty cycle, 1 minus d. So this means that we have this expression, 1 minus d to the second power, if I take this expression that I have derived, times d times T VO over 2L. I forgot to put 2L here. I forgot to copy 2L at the denominator. Okay, so just to have an idea of the difference between this situation and the other situation, ILB and IOB, let's plot them as a function of the duty cycle. So this is a parabola, because we have d times 1 minus d times a constant. If we normalize everything, let me draw everything here. This is a parabola. When d is equal to 0, the parabola is 0, but also when d is equal to 1, the parabola is 0. The maximum is when d is equal to 1/2. And when d is equal to 1/2, the maximum is TV, let's call it ILB max. This is the maximum, which is equal to, we can just substitute, TVO over 8L. So this is the behavior. This is the limit between continuous and discontinuous conduction as a function of d, which means that above this we are in continuous conduction, and if the current in the average current in the inductor goes below this curve, we are in discontinuous conduction. Okay. Of course, we can do the same thing and plot IOB as a function of D. Of course, IOB is equal to ILB times 1 minus D. So if I plot just only qualitatively, it's something that, of course, it's almost equal to ILB when D is close to 0, and then it goes rapidly down to 0. It goes more rapidly down to 0 because it has this quantity 1 minus d to the power of 2. Okay. Again, as I mentioned already in the case of the buck converter, we always have this situation in which the DC-DC converter passes from continuous to discontinuous conduction, because as soon as the load requires less current because it goes in a standby mode, for example, the current drops rapidly, and then the converter has to pass in a completely different mode of operation. Okay. finally, on this point, let's see more in detail what happens in the situation of discontinuous conduction. Now, the situation, if we consider the current, is pretty clear now, in the sense that we have to consider three different situations. During T on, the current goes up, again, as we have already discussed. This is T on, that is equal to the duty cycle times T, the current goes up. The derivative of the current is dIL over dt is equal to V in over L. Okay? Then we have a negative slope, during which the current has a derivative that is equal to V in minus VO over L. We have already discussed. But now, we are not at the end of the period. What happens is that, of course, here the current cannot go negative because it has to pass through a diode, and therefore it cannot go negative. When it tries to go negative, the diode goes off, and then the current goes to zero until the end of the period. So again, we have this situation of non-conduction. And therefore, we need to split the T off in two different periods, one that we call delta 1t and another one that we called delta 2t, because of course what happens is different. During delta 1t, the derivative of the current is the one that we have written here, and during the time delta 2t, the current is zero. The current is zero, the switch is off, and the diode also is off. Okay, let me write here, switch off, diode off. Of course, here instead we have switch on and diode switch off. Just for completeness of information, but the diode is on, and during T on, by definition, the switch is on, and if you remember correctly, the diode is also off. So these are the three situations that we have. Of course, now it is pretty easy to understand what happens. We have simply to write the total variation of the current in a period. Again, the total variation is zero because the current is periodic in stationary conditions. So we start from zero. Let's say total variation of the current IL in a time period, and therefore we have 0 is equal to the variation during T on, which is V in over L times T on, plus the variation of the current during delta 1t, which is V in over V in minus VO over L, this is the derivative, times the duration, which is delta 1t, plus 0, because of course this is 0. So from this we can pretty quickly write the dependence of V in over VO. Again, we can put VO on the left hand side here, VO times delta 1 times D is equal to, and we collect all quantities with V in, we have V in times T times delta T plus delta 1, D plus delta 1, okay? So we can eliminate T, and therefore we have VO over V in is equal to D plus delta 1 over T. Okay. Okay, no, sorry, D, not T. I was thinking about delta 1. Okay. Okay. Yes, there is another consideration that we can also make, and it's the following. This is the ratio of the output voltage to the input voltage. If you look at this this situation, if we consider that all these quantities are ideal, you should see that we have no power dissipation in the inductor, in the diode, because we are assuming that the voltage drop on the diode is 0, in the capacitor, and also in the switch. So this means that the average input power has to be equal to the average output power. And therefore this means that if we call, for example, here E in as the average input current and I/O as the average output current, the product of V in times I in, which is the input power, has to be equal to the product of VO times I/O. Okay, this is in the assumption of no power consumption in the middle. But of course, all the elements are not elements that dissipate any power. And if we do this consideration, then we can write here V in times I in is equal to VO times I/O, which implies that VO over V in, VO over V in is equal to I in over I/O. And therefore, this quantity that we have written here can also be I in over I/O. I in is the average current in the inductor, also because the input current is also the current in the inductor. Average current in the inductor. So we can plot it here, and we can also evaluate it now. So I in is equal to what? By definition, we can is equal to the average value of IL, and by definition we can compute the area, the integral of IL over T, and then divide by t. So this is the integral, let me write it completely, the integral of IL in the period and divide by the period. This is just a definition, okay? The integral of the IL is this area. That is easy to write because it's a triangle. We can compute the area as the base times the height divided by 2. So the base is d plus delta 1 times t. The height is I peak that we have already computed is V in over L times dt, and then I have to define, so this one times this one, and then I have to divide by 2, and then by t. That's it. Now this is the average expression. We can make some simplifications. Let me just do some simplifications. That's the only thing we need to do now. And okay, now let me, okay, and let me continue. And now we can use this expression to obtain IO. So from here I can obtain IO, which, if I use this expression, is equal to delta 1 over d plus delta 1 times I in. Okay, so simply I can use this expression and substitute here, and you should see that I'm able to simplify almost everything. I have V in over 2L times T. Okay, now we are almost there. We need to make some simplifications here. Let me do it with the help of this part of the expression. What we can do is the following thing. Let's use this expression. Let us do the following thing first. I'm copying this expression. The important expressions I want to copy in the next page. To polish a little bit the things here. One. And the other one that I want to copy is this one. Okay. Okay. Now I just want to write it in a simpler way. Let's write it like this, and therefore what we can do is the following thing. We can divide by d and multiply by d, and then we can also divide by VO and multiply by VO. Okay. Once we do that, we can substitute this expression with this one, which means basically consider that delta d over delta 1 is equal to VO over V in minus 1 let's say minus V in okay, and therefore delta 1 over d is equal to V in over VO minus V in. Okay, so that I can substitute here. So, and this other expression can remain here, and that's it. Okay, let me copy everything. I can substitute this expression with this one. I have V in over VO minus V in, this quantity, times D square times V in over VO times T VO over 2L. So this is just to show you the following thing, that in this case what we have is a dependence of the current in the output load as a function of the ratio of the input voltage to the output voltage, which is here and also here, the duty cycle, and the input voltage. So the current only enters here, and therefore if I want to consider at fixed everything else the dependence of D on the output current, I have something like this. This is proportional to the square root of the output current. Okay, at V in and VO fixed. So just should let's say pause to consider one thing. This was a constant in continuous conduction. At V in VO fixed, D was absolutely constant. Instead, in conditions of discontinuous conduction, D is proportional to the square root of the current. So just to summarize everything, we can just look at the dependence of the current of D as a function of the current. The plot D as a function of the output current at the boundary from continuous and discontinuous conduction was like this. It is something that we have already derived. So this was continuous conduction. And this was discontinuous conduction. This is something that we have already plotted. I just have exchanged the axes. In continuous conduction, D is independent of I/O. At constant V in and VO, D is a constant independent of I/O. It's like this. So this is, for example, you remember that VO over V in is equal to 1 over 1 minus D. So once VO and V in have been fixed, D is fixed. For example, if VO is equal to twice V in, then D is equal to 1/2. So this is VO, for example, VO over V in is equal to 2. And so on. These are for different values of the ratio VO over V in. When we are in discontinuous conduction, instead, D is proportional to the square root of the current. So it has this expression. Of course, at the boundary between continuous and discontinuous conduction, the two lines must be connected. And then, of course, this must pass through the origin. So let's say a square root has this shape, and therefore this is what we need to do. So this is from the point of view of the operation of this circuit, it's pretty, let's say, critical, this issue. If we change rapidly the current through the load, we need to change at the same time very rapidly also the duty cycle. Because, for example, if the output voltage must be double the input voltage, and you have huge variation of the load, of the current absorbed by the load, then you need to change rapidly the duty cycle when you change the current. Okay, so these are pretty basic plots that describe the operation of the buck converter and of the boost converters. Okay, we can make a break here.